Hi, everyone. So today we have Ashok from Boston University speaking, and he's going to be telling us about online to batch conversions and differential privacy.
Okay, thanks. Yeah, thanks for the opportunity to speak. My name is Ashok, as said. This is joint work with my students, Chinsu and Huang, who are both PhD students at BU. Okay, so the talk is about differentially private online to batch. Start with some intro, hopefully. Why is it not changing slides? Okay, well, change. Okay, so I imagine anyone listening to the talk probably knows roughly what this talk is going to be about in some sense, but we're going to, in a high level, be talking about privacy and learning. So just so we're on the same page, we want to learn something from user data. We want to use this to build some sort of useful products. So here, for example, YouTube has decided, based on my previous watch history, I guess, to recommend various videos to me. Right? But the problem, of course, is that we don't want this learning process to compromise user privacy. So like one attack vector one might imagine is that a user could be able to learn about other users from looking at the outputs of their model. So let's sort of, as one example of how these two goals might seem kind of, maybe in tension a little bit, is that you could imagine you're building some sort of snack recommendation machine. And so you have a bunch of people. Several of them have some red feature, several of them are purple, and maybe one of them is green. And the red people all say they like popcorn, the purple people say they like ice cream, and the green one says they like chips. So then when another user comes along and asks your model what snack should they eat, if this user was green, it might be reasonable from a learning perspective to tell them that they should eat a chip, right? That really is the best match for their sort of feature in your data set. But of course, then this person might turn around and say, ha ha ha, I actually don't really care about what to eat. I'm just here to figure out what is the favorite food of this one green person in your data set. So now I can go to the store and like buy all the chips up so that they're sad or something like that, right? So we want to avoid this kind of behavior. By the way, can you guys see my mouse? If I gesture with that, is that
Yep.
Okay, great. Okay, so high-level intuition, right? We want to sort of learn common trends from a data set and not individual quirks. But here, it's a little bit actually more difficult than that. We want to only learn common trends that are really justified in the data set. So even if it happened to be the case that, say, all the green people really do like chips, we don't have enough information yet to really justify that. So we would still be leaking private information by revealing what is really a common trend, but could have been an individual quirk based upon the information we had in that small data set. So more formally, of course, we have some notion that we have a data set and maybe a set of prediction algorithms or a hypothesis class or something like that, depending on how you want to put terminology on these things. And our goal is to output an element of this hypothesis class such that the process of choosing that output is differentially private, or some other notion of privacy, whatever you want. And that also, if the data set happens to be IID, then the expected performance of your output should be good on new examples. And importantly, of course, the first consideration is a sort of worst case thing, right? You want to be robust to the possibility that somebody is arbitrarily injecting stuff into your training set and still be able to ensure some amount of privacy on the people who aren't being arbitrarily injected. And the second one is a little bit more sort of optimistic, right? You're saying like, look, if there is something to learn in this data, if it does describe some distribution that I'm interested in, then I would like to learn that information, right? So first one is arbitrary worst case. The second one is if the data has some nice property, I'm going to learn that property. But if it doesn't, then all bets are off. Okay, so what does this talk about? That's sort of the background. One observation that, at least in my opinion, seems to be true is that if you want to build an optimal privacy-preserving algorithm, that is one that sort of learns as fast as possible or as efficiently as possible and still maintains privacy, it's a little bit hard to do. You have to kind of think very carefully about how you're building the optimization algorithm, how you're incorporating privacy in order to do this. But in contrast, at this point, designing non-private algorithms is actually kind of easy. There's a lot of tools that we have at our disposal now that make it relatively straightforward, I would say, to put together an algorithm that is that is getting an optimal convergence guarantee, but doesn't preserve privacy. It's like, maybe you could write down a full proof of such a thing and maybe 10 lines of algebra if you wanted to. So we want to kind of bridge this gap. So we want to build a method such that you can design an optimal private algorithm just by taking a non-private algorithm and sort of doing something to it. Right? So you want to do something to a non-private algorithm to make it private in such a way that the optimality guarantees are sort of preserved. An optimal non-private algorithm will be converted into an optimal private algorithm. Okay, so that's sort of the goal of this talk. We're going to basically describe a procedure for doing this. Okay, so let's formalize things a little bit so that we can talk more precisely about what this means. So the notion of optimality in terms of learning, right, we're going to characterize in terms of stochastic optimization. So most of the learning problems out there, I would say, can be modeled in this way. And it's a framework that has roughly 3 ingredients. So we need a data set that is, say, Z1 to ZT, a size T data, where each of the Z's you can think of as being, say, a feature vector, comma, label pair, or something like that. And then we also need some parameter space of models. So W, we'll call, which is some subset of d-dimensional space. And then finally, a loss function, which will tell us what is the loss of using some parameter W on some example Z, and that will give you, of course, a real number. So, a typical example might be, say, logistic regression. W represents the weight vectors, Z is a feature vector label pair, and so L would just be the, sigmoid plus log loss on that weight vector feature pair. So the goal is then to optimize the population loss, which is the expected value of the little l loss on a fixed W over all of the random Z's. And so we call this capital L. This is the population loss. If we do well on this objective, then we consider ourselves to have sort of learned whatever data there is in the task. So because I want to actually describe very, very good convergence guarantees, we're going to also assume that everything is convex. So instead of just an arbitrary parameter space, we're going to assume that W, capital W here, is a convex set. And I'm also going to assume that the loss function L is a convex loss function. Obviously, you might want to work with a non-convex case, but that's maybe for a different talk. Okay, so that's what we mean by learning. We're going to sort of solve this stochastic optimization problem. So the whole goal then is private stochastic convex optimization, where here we want to design a mechanism, which is some M, some randomized function that takes as input the data set and outputs some random element of the parameter space W. And this mechanism should be epsilon delta differentially private. And actually in the paper, we work with RDP. You could imagine trying to do this with some other measure of privacy. In this talk, we're going to sort of just use epsilon delta just for familiarity. And then we want to have it be the case that if it so happens that the data set is some IID sample, then it should be the case that this the population loss evaluated on the output of the mechanism, so at the parameter that the mechanism outputs, should be sort of as close to the minimum possible population loss as possible, right? So here, this expectation is kind of there's a lot of things to unpack. This expectation is expectation over both the randomness in the Z1 to ZT, because now we're assuming that they're an IID sample. It's also randomness over the mechanism M, which is needed to ensure privacy. And then the capital L itself is already an expectation, right? There's a sort of internal expectation there over some dummy new out of sample data set data point Z. Okay? So there's really sort of 3 expectations in this definition. I'm going to call this difference either suboptimality gap or an excess risk, depending on whichever term comes to my mind quicker when I'm talking. So they're the same thing. Okay, and stop me if there's any questions about any of this. Obviously, if the first part is unclear, then it's going to be hard to get onto the later parts. Okay, so a typical strategy for solving this problem is something like DP-SGD. So how does this work? You start with any kind of iterative non-private algorithm, such as stochastic gradient descent. And these algorithms tend to access the data by looking at gradients. So we'll look at, given some iterate WT, will evaluate the gradient at one data point zt, and then we'll use that gradient in some way to produce a second iterate wt plus 1. And maybe the simplest way is SGD. We just add the gradient to the previous iterate, but you could do something more complicated, like whatever Atom does or something like that, some sort of more intricate stateful update. Doesn't really matter. The point is that the data is only accessed through this gradient. And that means that in order to make this algorithm private, all we have to do is make this gradient somehow private. So we apply something like the Gaussian mechanism, which just adds Gaussian noise to the true gradient to get some sort of noisy gradient. And so now this noisy gradient is somehow fuzzed in some way that makes it a private estimate of the real gradient. And so now the whole algorithm will become private via some post-processing. You do operations to private things, they stay private. Okay, so this is DP-SGD. It's a fairly intuitive thing to do, right? How would you come up with this? You would observe first, hey, there's a lot of non-private optimization algorithms out there, so I can just choose one and then process its inputs in some way to make the whole thing private. And this is appealing from a sort of an engineering perspective, perhaps, because you can have kind of two engineering teams. One of them, its job is to produce better non-private optimization algorithms. They don't have to worry about privacy. The other one, their job is to produce better ways of privatizing things like gradients, and they don't have to worry about optimization algorithms, at least so much a priori. And this has the advantage that you can sort of use this modularity to improve things, right? Like if the optimization team says, hey, you know what, I've discovered this algorithm Atom, it's really, really good, we can just use that, right? And it'll make the algorithm presumably perform better overall while maintaining privacy. So at the end of the day, this DP-SGD procedure is actually fairly straightforward to analyze, I would say. And it uses any base algorithm. So you can swap out SGD for Adagrad or Atom or AMSgrad or whatever you like. And the whole procedure still works well. Unfortunately, though, it doesn't get the optimal convergence rate usually. So you may be able to say in some particular nice settings it might do well, but in general, you can't really show that this is going to have the correct convergence rate. And that's kind of disappointing, right? As a theorist, you might say that's a no-go. I have to get the right rate. So what can we do instead, right? We want to get the optimal convergence rate. And first, there's some question, what does it mean to have the optimal convergence rate? What does optimality mean in this setting? And there's kind of two different directions, right, that you could imagine. One of them is that maybe you should be optimal in terms of the data set size. This is sort of a sample complexity measure of optimality, where you're saying that given a certain amount of data, I would like to make the excess risk as small as possible. I don't care how much time it takes. And then the other version is in terms of running time, I'll take as much data as I can, but I want to make the sample complexity as small as possible, as fast as possible. It turns out, fortunately for us, that it's possible to achieve both notions of optimality simultaneously. So there's no trade-off that we're going to have to worry about here. We're going to just be able to be optimal both in terms of sample size and running time at the same time. So the way that one does this is typically by sort of rethinking how you're doing the optimization algorithm itself to incorporate privacy throughout the procedure. And I don't want to go into too many details of how this is done in the past, but I'll just say there's one example here is you can sort of combine three types of ideas. One of them is the Gaussian mechanism, which is maybe a little bit more familiar, and the other two require a little bit more fine-grained thought. One of them is SGD. You have some very intricate analysis of SGD with variable batch size to say something about the last iterative convergence. And the other one is this privacy amplification mechanism called amplification by iteration. And if you sort of put all these three ingredients in a pot and stir them and cook them very, very carefully, you can design this algorithm that was originally called Snowball SGD. And you'll be able to prove this following result, which is that if you assume that the losses are smooth, Lipschitz, and convex, and that the W has the parameter space W has some diameter, then there is an epsilon delta DP algorithm that runs in time OT, and its excess risk is bounded by some DG over root T. And for now, let's not think too much about the DG. The important property is dependency on T, plus some DG root dimension log 1 on delta over T epsilon. Okay, so again, let's focus mostly on the T dependence for here. I'll put the whole thing up just for completeness references, but I think it's better to just think mostly about the T and the epsilon. So here it's a 1 on root T plus 1 on T epsilon. And it turns out that this bound is optimal in both settings that we talked about before. It's optimal in terms of the sample size t, and the linear running time is also clearly optimal, right? If you have a data set of size t, presumably it will take you t amount of time to actually look at every element. So let's unpack this bound just a little bit. It turns out that the optimal rate without worrying about privacy, so the worst case optimal rate for a non-private stochastic optimization, is already 1 on root t. You cannot improve upon this. So the optimal private bound then can be decomposed as some non-private thing plus some kind of price of privacy, right? So this t epsilon part is a term that is telling you how much you lose for being a private algorithm. And you can sort of look at it and immediately see that for not too small values of epsilon, this term is kind of free maybe, and you look at only the private bound. But if epsilon does get too big, then you will start having to pay this price more. Okay, so this is the sort of second technique that one can use. And just to summarize these two ideas, the DP-SGD method, its analysis, I would say, is fairly straightforward. It can use any base algorithm fairly easily, but the convergence rate is not the right thing. On the other hand, you can use some sort of custom algorithm design. The analysis, again, this one is subjective configuration, but to my mind, the analysis is somewhat harder. And you have to be very careful with it. You can't just easily tweak any part of the analysis and hope that it'll work. You have to carefully do what the right path of algebra is. So you can't just sort of plug in any base algorithm, and like any improvement on a non-private algorithm will not necessarily translate to an improvement here, but the convergence rate is optimal. So we'd like to kind of thread the needle here, where we want an algorithm that will use any base algorithm. So if you improve the non-private analysis, you'll be able to also improve the private analysis. And in particular, we'll be able to get optimal convergence rates. I would like to say the analysis will also be easy so that we really get the best of all things. But I think that would be a bit of a stretch. So let me say that the analysis is maybe medium hard, let's say. But that's subjective. You don't have to agree with me on this one. I think this is the more objectively true statement. Okay, so again, at a high level, what we're going to do is take some non-private algorithm that has an optimal sort of worst case convergence guarantee, and then we'll be able to generate from it a private algorithm that also has the optimal worst case convergence guarantee, but now is having the optimal private worst case convergence guarantee. The running time will be the same, so we'll not incur any significant overhead in terms of running time or space complexity or anything like that. And the really importantly valuable part about this result, I would say, is that the private algorithm can somehow capture some of the flavor of the non-private algorithm. So this first point is talking about worst case convergence guarantees. But the real world is frequently not worst case. And there's a huge, like almost cottage industry, I would say, in the optimization, the non-private optimization community, building algorithms that go beyond worst case analysis. Something of the form, if the data happens to be easy in some way, then I'll do really well, even if I still have the correct worst case convergence guarantees. And so we would like to build a private algorithm that has the same kind of property, which is called adaptivity. If the data happens to be easy in some way, we'll automatically perform much better. And that is intuitively even more at odds with privacy, right? We're still extracting even more information from the data set that could leak privacy in order to detect the possibility that it is, quote unquote, easy, whatever that means. Okay, so high level intuition, right? We want better non-private algorithms to imply better private algorithms. Okay, so how are we going to do this? There's sort of 3 key ingredients that we're going to need. The first one is online optimization or online learning. The second one is this thing called anytime online to batch conversions. And the last one is tree aggregation. And so my guess is that ingredients 1 and 3 are maybe relatively familiar, or there's some reasonable chance you may know about them. Ingredient 2 is maybe a little bit less familiar. But we're going to sort of go through all 3 of these and see how to put them together to achieve the result that we want. Okay, so first, what is online optimization? So it's been in many things, sometimes online linear optimization, sometimes online learning. I put all of them up in the name of the slide there. It's, in my opinion, I would say one of the most popular ways to build stochastic optimization algorithms. So when I said in the very beginning that it's easy to build non-private stochastic optimization algorithms, this is what I meant. It's sort of building online optimization algorithms is somehow relatively well understood at this point. And so, and it's actually fairly easy to build stochastic optimization algorithms using these online algorithms. And you don't have to just take my word for it. If you look at a lot of sort of popular algorithms in practice, they all were actually originally built as online optimization algorithms. That's how they were sort of originally analyzed. So we're not going to look at these complicated algorithms, though. We'll only talk about gradient descent, basically. And so what is online optimization? So it's a game that we play between a learning algorithm and an environment for capital T rounds. In each round, the learning algorithm will choose a vector WT in the space W. Then the environment will choose a loss vector GT that's in RD, and the algorithm will suffer a loss that's the inner product between the two. The goal is to bound this thing called the regret, which is the total loss suffered by the algorithm minus the total loss suffered by some constant fixed comparator point U. So it's just this linear sum. That's if we make this sum small, then we'll say that the algorithm is doing well. It has low regret. It's a good online learning algorithm. And the important thing to notice about this setup is that we make no assumptions about how the GT is generated. They could be coming from some kind of IID process, or they could be coming from some fairly evil adversary, perhaps, that looks at the WT that the learner produced in step 1, and then specifically chooses GT in such a way as to make this regret as high as possible. That's allowed, right? We don't want to assume anything about how the GT is generated. Could be anything, and this makes the problem simultaneously harder, but also gives algorithms that solve it well a lot of power because they're very robust to sort of arbitrary perturbations to their inputs. Okay, so the most basic online learning algorithm is online gradient descent. It's very simple. It looks just like regular gradient descent. You say WT plus 1 is the previous choice of the online learner, WT, minus some learning rate times the previous cost vector GT. Right? So WT minus GT. And then we're going to project the whole thing via Euclidean projection into the space W. So we're on projections. I put this on the slide to be completely correct for at least for one slide. But for the rest of this talk, I'm going to completely forget about projections because I think they just make the notation complicated without actually helping anybody understand what's going on. So there will be no more projections, but if you look carefully, you can sort of see where they're supposed to go. Okay, so the key result about online gradient descent is that if all of the gradients are bounded by some G, and W has some diameter D, and you set the learning rate appropriately. So again, don't care too much about this D and G dependence. What's important to notice is that the learning rate eta needs to be roughly 1 divided by square root of T. If you can do this, then this will ensure that the regret is always bounded by D times G times square root of T. Again, let's not worry too much about this dependence here. Let's focus on the square root of T.
There's a question in the chat.
Oh, sorry.
Why is the regret the inner product of W and G?
Why is the regret the inner product? So this is sort of I'm just defining it this way. Like this is, at the moment, it's some sort of abstract problem that we might want to solve. It's not really clear what it's for yet. It turns out that eventually we're going to make GT equal to gradients. And then by some sort of, by some consequence of convexity, this difference here will be an upper bound on the excess risk between WT and U. So that's why we want inner products. It's because convexity allows us to relate inner products with gradients to function differences. But a priori, it's just sort of some random definition. This is a game that you could play. It's sort of clean to define. Whether or not it's useful is maybe a different question. Okay. So this square root of T is the regret that we're able to gain, and this is minimax optimal. So what does that mean? It's possible that there could be some U's, and there probably are, right? Some values of U for which this RT of U is actually less than DG root T, right? Like if you look at this, the left-hand side is a function, and the right-hand side is a number. So what we're saying is that this function for all U is bounded by this number. So that means that for some U, it's probably less than the number. So when we say it's minimax optimal, what we're really saying is that any other algorithm you pick, it might, for some U, get a smaller regret bound. But there will be some sequence of GTs and some U for which its regret is at least this amount. So you can't beat DG root T all the time. So this is online learning optimization. And then to the question that was just asked, why are we doing this? Why do we have this inner product? What's the point of this? It turns out that there's this sort of very classic result called the online to batch conversion. So the online to batch conversion says, look, online learning requires that you have some process, doesn't specify what process sets what the GT should be. So I will tell you to set the GTs in this way. Given the iterate WT of the online learner, I will set the GT to be the gradient of the loss at using the teeth example in my data set. That defines an environment for an online learner. So then I can run the online learner and get all of my iterates, and I'll compute the average of them, W hat. And then there's this theorem that says that the suboptimality or the excess risk of W hat with respect to any point U can be bounded as the expected value of the regret divided by T. So if you happen to obtain the root T regret bound that online gradient descent would obtain, then this result becomes order 1 on square root of T, which is, it turns out, also optimal for stochastic optimization. And I would like to point out here, in this type of result, in regular online learning, the U is some arbitrary comparator. It could be any point. But when you start thinking about online to batch like this, you should think of U as being the argmin of the L. Right? That's sort of the U that makes this left-hand side as big as possible, so it makes this bound as useful as possible. And so this bound, this statement is really what drives interest in online learning to a large extent, I would say, because this bound allows you to fairly easily generate a 1 on root T, which is an optimal stochastic optimization guarantee. And surprisingly, it turns out that even though online learning has this kind of adversarial GT flavor to it, it's weirdly easy to build algorithms for it. I would say easier to build algorithms for online learning than it is to directly try to solve this stochastic optimization problem. Part of that is because the simplicity of the setting just lends itself to maybe easier time to think about it, right? If you start thinking about stochastic optimization, maybe you start worrying about, martingale sequences or something like that. It becomes a little bit hairy. But if you just focus on this almost combinatorial optimization problem of online learning, life, for some weird reason, tends to become easier. Okay, so here's a picture of online to batch conversion in action. Here, the red points are the iterates of online gradient descent, and the green points are the averages. They're the averages of the red points. So here, we started out over here. We get the gradient for some loss function whose contours are these circles. We move over here because the gradient has some noise, right? It doesn't point directly towards the minimum. We sort of end up, gradient descent is going to kind of move around this optimal point a little bit, maybe not quite get into the center, whereas the averages are going to be a lot more stable and move in towards the center. This is the online to batch conversion, also known as SGD with Polyak averaging, sort of been rediscovered in a variety of different contexts by different people. Okay, so now that we know this, let's sort of make a straw man algorithm. What if we just try to privatize this algorithm using, say, the Gaussian mechanism? So some simple thing. It's basically the same as DP-SGD. So spoiler alert, yeah, this will not work, but it's a good idea to sort of see how we would do this. So we would start by maybe defining the GT the same as in the online to batch conversion, but then we would update WT as the old W minus eta GT, and then we maybe add some Gaussian noise with an appropriate standard deviation. The idea here is that doing this update will privatize WT plus 1 so that the whole thing will become private. And then at the end of the day, we're going to again return the average of all units. Why does this work? Well, if we know that the capital G, the little GTs are less than some capital G, then the sensitivity of WT plus 1 is at most eta times capital G because it's WT minus eta times GT. So if we add this much noise by sort of standard privacy analysis, then we'll be able to make the update private. And this obtains a bound if you sort of calculate through what the effect of the noise is on the convergence guarantee. So obtain a bound of 1 on epsilon root T. So the right bound would have no epsilon here. Here we have an epsilon, which is the price of privacy. And in fact, you can do better. If you sort of use the sort of fairly straightforward mini batching argument here, you can easily improve this to square root of epsilon times T. Okay, so we can move the epsilon inside the T. But nevertheless, it's still not the right bound, right? The right bound would have been square root of T with no epsilon, and then plus a 1 on epsilon T out here. Okay, so we can do this, but we don't get the right result. So high level, what's happening? Well, in this sort of analysis, we started with WT, and then we observed that the difference between WT and WT plus 1 is on the order of the learning rate. It's the order of eta, which is order 1 on root t. This is saying that when you do something like gradient descent, the sensitivity of your next iterate is order learning rate. That means that you have to add noise that's on the order of the learning rate in order to privatize everything. That's a relative, what is the back of the hand calculation for privacy, right? Is you need to add noise that's proportional to the sensitivity of a system in order to make it private. And that's bad because this is sort of too much noise. It destroys the convergence analysis. And we could try to fix this by making eta smaller. Right? If we make the learning rate smaller, we'll have less sensitivity, so therefore we can add less noise. But then that will make the convergence analysis of gradient descent work less good. Right? So there's just too much noise being added to the system because the iterates are too far apart. So how are we going to fix this? Well, let's try to change things in such a way to make the system less sensitive, right? So that this 1 on root t becomes something smaller instead. So how are we going to do that? Well, we're going to move beyond the online to batch to this other thing, the anytime online to batch. So I developed this a couple years ago for some totally different reason, but it actually will have a very nice application in privacy here. So how does this work? It's a very, very small change to the regular online to batch. We have some iterates, W1 to WT. I'm going to define W hat T now to be the running average. So W hat T is not the is not the Tth iterate, it's the average of the first T iterates. And now the key change is that we're going to evaluate GT not at WT, but at W hat T. So we evaluate the gradients not at the current iterate of the online algorithm, but at the average of all the previous iterates. And if you do this change, then it turns out that the same convergence rate is true. The suboptimality gap is still bounded by the regret divided by t. In fact, this is actually a loose analysis. You can tighten it a little bit. There's a sort of a negative term out here, but we don't care about that for now. So in some sense, you can think of this as kind of running gradient descent, but lying, right? If you're running gradient descent here, you might think that, oh, I want to get the iterate at WT, but I'm going to lie to you and give you the iterate somewhere else. And this is why online learning, the sort of adversarial nature of the problem, is very useful. Because, again, remember, we didn't assume anything about the nature of GT. They could have been anything. So the online learner is still perfectly capable of producing its regret bound, even though these GTs are now much less obviously related to the actual iterates WT. So just to contrast this with the classical online to batch, it's almost the same. The only difference is that we evaluate the gradient not at WT, but at W hat T. To put this into sort of pseudocode, right? If your online learner was online gradient descent, the full procedure here would have been compute W hat T, and then, which is the average, compute the GT, which is the gradient, at W hat T, and then update WT minus eta times GT. And again, here, the only difference between regular stochastic gradient descent is that this GT is now evaluated at this average instead of at the actual WT. Now, if I didn't tell you that this thing has a good convergence bound, you might think it was sort of obviously a bad idea, right? Because we can draw a picture like this. So here, the red iterates are the iterates of our online gradient descent, and the green iterates are the running averages. And so the red iterates, they start out going sort of the right way, but now you can see they're kind of overshooting the optimum and just sort of going up and off to the top for no reason. But really, that's sort of expected behavior, because the green iterates, the running averages, are naturally lagging the red iterates. So they haven't gotten to the center yet. So the gradient down here is still pointing up, which means that the update over here, which is using the gradient at the running average, should still have a gradient pointing up, so it will continue to go up. Right? So by doing this weird procedure, we're sort of expecting to wildly overshoot. But nevertheless, there is a theorem that says it works, so we can actually try to do some very simple experiment to see that this is indeed not such a bad idea, right? So here is the a simple example where I'm computing the I'm running on an absolute value of x minus 10 as the loss, so it's a one-dimensional problem. The loss function is just x minus 10, so I'm trying to go from 0 to 10 basically, right? And I added some noise to all of my gradients. So here we're looking at online gradient descent, sort of jitters around the correct value of 10. And regular online to batch says, oh, look at the average of all your iterates. It will converge, and indeed it does, towards 10. That's sort of smooth. Okay, so that looks fine. What about the anytime online to batch? Well, this graph will look kind of wild, right? So we have the anytime iterates of gradient descent, the online learner is actually indeed, as we see, overshooting wildly, right? It's doing this horrendously weird high amplitude oscillation stuff. But that's actually kind of irrelevant, because this is just some internal state of the optimizer. What really matters to us is the green iterates, the iterates of the running averages. Right? And so the running averages, you see, actually very quickly reach 10. And they also have some oscillatory behavior, but it's very, very quickly damped out. And if we flip back and forth between these, you can see that the green iterates are actually the best thing. Right? Even though the algorithm looks dramatically strange, it actually performs pretty well. OK, so that's all nice, but why do we care about this? Why is it important for privacy? Well, if we look at what this algorithm is doing, we're querying gradients at the running averages, W hat. This means that the only influence the data has is the only place we access the data set. We only access the data set at W hat. And if you look at W hat, it actually has really low sensitivity. So if you look at the difference between two successive running averages, sort of a fairly straightforward algebraic calculation. Actually, I think this should have been a t plus 1 down here. Sorry, so the sensitivity is even lower than I'm mentioning. But you'll see that the difference between two running averages is roughly order 1 on t. Okay. So this is actually fairly low sensitivity. And not only that, it's very robust. Right? It doesn't matter what the online learner does. This WT plus 1 here didn't really, that's what the online learner is doing, and it doesn't matter what it does. We'll always have the differences of running averages are always O1 on t, so long as the learning iterates are bounded, which we're assuming because of our bounded domain. So this is the key property of anytime online to batch that's going to make it help for privacy. It's drastically reducing the sensitivity. And now I'm going to sort of, again, make a kind of cheating thing here. And I'm going to, for the rest of this talk, pretend that this t over here is a capital T. Okay? Yes, it's not quite true until you've gone a certain number of sort of burn iterations, if you like. But I think it captures all the intuition to think of it as capital T. I will say, quite honestly, that the way when we designed the algorithm, we did think of it as capital T until we got to sort of near the end of our analysis, and then we sort of went back and patched things in some sort of some simple algebraic trick that makes it okay that it's not quite capital T. So we'll just think of it as capital T. Okay, so to summarize, the classic online to batch has high sensitivity. The sensitivity depends on the learner itself, and if you try to make it lower, you'll destroy the convergence bound. The anytime one does not have high sensitivity. It has really low sensitivity that does not depend on the learner. And sensitivity is order 1 on t rather than order 1 on root t. So it's quite a bit lower, and it's quite a bit more robust in terms of its sensitivity. So that's great, right? Low sensitivity means we need less noise to make things private. This gives us a clear wedge to drive to try to get a better privacy guarantee. So just as the picture right here, we have W hat t, the W hat t plus 1. Their distance is order 1 on t. So you might imagine that the right thing to do is just add some noise to W hat t of order 1 on t epsilon. And I really wish that were the end of the talk right now. I could just say, yeah, you do that. Everything is fine. We're all done. And it might work, to be honest. But unfortunately, we couldn't show that this is actually all you need to do. So we do need to do a couple more tricks in order to sort of take advantage of this low sensitivity. So how are we going to do this? Well, if you're familiar with variance reduction, the following sort of approach may seem intuitive. And if you're not, well, hopefully it won't seem too bad. So we're going to write the gradient at WT as sort of a telescoping sum, the gradient at the previous iterate plus the difference in the gradients at the previous two iterates. So we're just writing the gradient and some sort of difference of the previous iterates. And now if we assume that L is smooth, then the difference in the gradients between these two iterates can be bounded by the difference in the iterates themselves. And we already saw the difference between two successive iterates, or two successive running averages, is order 1 on t. So how do we take advantage of this? I'm going to define my GT, or I guess because of weird summation indices, I'll call it G tau for a minute, which is the sum of all of the previous gradient differences. So I'm taking advantage of that. If I unroll this recursion for all t time steps, then I can define this GT to be a reasonable estimate of this true gradient at WT. And each of the terms in this sum I know is going to be small by this calculation. So the picture, right, we're sort of looking at the optimization path of my algorithm, and I'm kind of trying to integrate along this path what the differences in the gradients are to compute the gradient at this final point. And importantly, as I do this integration or do this summation, each of these terms that I'm adding up are very small. Okay, so how do we take advantage of this? Well, we were seeing that GT in expectation, you just, by unrolling some sort of telescoping sum, you can see that its expected value is going to be the gradient at the actual iterate. The variance of GT is also very small because the variance of each individual sum is order 1 on t squared, because this thing is order 1 on t in terms of its magnitude. So the whole thing is order 1 on t, its variance. So the variance is a very, very high quality estimate. So what's our strategy going to be? We're going to define GT as this sum of all these different gradient differences. Then, in some yet to be determined way, we'll make a private version of GT. Then we'll update using this private version of GT. We'll provide that to the online learner. And then there'll be the end. We'll compute the next running average to repeat the procedure. So if our learner happens to be online gradient descent, this will be our update, but we don't care what it is yet. It could be any learner. So there's still a weasel part here. How do we generate this private version of GT? And this is where we're going to use tree aggregation. So if you look at the expression for GT, it's actually a sum of a bunch of terms that all have low sensitivity. In fact, you can write GT as the previous GT, GT minus 1, plus 1 incremental update. So this is what I'd call an incremental sum statistic. It's sort of a running sum that you need to output. And it turns out that there's this thing called binary or tree-based aggregation mechanism that basically solves this problem, how to privatize these sums. Basically, given the sequence of GTs, we can generate a private sequence, G1 hat to G hat T, that is private and also is very, very close to the real G. Right? So the difference between these two things is order 1 on T epsilon, Y1 on T, because each of these individual terms has sensitivity 1 on T. Okay, so that's our whole strategy. We're going to define the GTs in this way. And we're going to define a private G hat T via tree aggregation. And we'll update our online learner, whatever it is, using G hat T. So this could be any online learner update again. But for concreteness, if you want to think of a particular one, online gradient descent would do this update. And then we compute the next running average, and we're able to repeat the process. This is the whole algorithm. And the privacy guarantee is now immediate from tree aggregation and the stability of online to batch. Because we made these things by these running averages, these are low sensitivity, so the privacy guarantee just follows. There's one final loose end, which is to check that it doesn't mess with the convergence guarantee. This is actually a fairly straightforward calculation. We can sort of observe these facts about the GT that we've already collected, and putting them all together, this tells us that the G hat T is very, very close to the true gradient. Right? Because the variance, square root of variance is 1 on root T, and then triangle inequality 1 on T epsilon. So now that we have this property, if you just sort of walk through the proof of the anytime online to batch, it turns out that you can get this sort of bound where the suboptimality is bounded by the average regret plus the sum of all these errors, which is going to be order 1 on root T plus 1 on T epsilon. Okay, so that's some calculation. It is a little bit annoying to do, but once you do it, you get the following theorem. So this is the full result. There's a lot of wall of text here, but basically this is all laying out the same assumptions. L is G Lipschitz, H smooth, and diameter D. Then we run this on anytime online to batch using these averages. We compute the GT using this sum statistic. We use tree aggregation. And then at the end of the day, we get a bound that looks like the average regret plus the privacy price plus this sigma D over root T. What is sigma? Sigma is the variance of the gradient. So it's the amount of noise that's sort of inherent in your system.
Hey, Ashok, Pradeep here. I had a question. So I probably missed the first part of the talk. But like when you get this bound, do you get a regret bound out of this? Like right now you're giving a SEO bound, but what is the regret bound you get out of this algorithm?
Oh, so this is a black box conversion. You take any algorithm that with any online learning algorithm and you plug it into this setting, and you'll get this SEO bound. So the regrets will be a function of the online learning algorithm you use. And in a minute, we'll talk about how to instantiate this with different online learning algorithms and see how you get improved results.
Okay.
Okay, so if we sort of unpack this bound a little bit, it's the average regret, which you get from sort of online to batch, plus the same privacy penalty, plus this thing, which is really a statistical lower bound. This variance term is measuring how much sort of inherent noise there is in the system. You don't know what sigma is. It's sort of hard to measure. But whatever it is, you cannot expect to do much better than this. So you shouldn't expect your regret to ever really actually improve upon this. Okay, So that's the result. And if you were to plug in online gradient descent as your bound here, this thing would be order root t. And so the whole thing would indeed get you the 1 on root t plus privacy penalty. So in fact, recover the correct asymptotics for private convex optimization.
Sorry to ask you again. So if I understand, your algorithm is an online algorithm, right? At the end of the day.
It's sort of online that we can release all of the iterates, but it's really we take an online algorithm and then we do something to it to make an SCO algorithm. It's not going to have. It'll only have a regret guarantee if the data happens to be IID.
So you get you get a stochastic regret guarantee. Because my question was the algorithm. It seemed like an online learning algorithm.
Right. So if you go back and look at this thing down here, right? Because we're evaluating the gradient at these different points and we're doing this weird thing, we'll have a guarantee on the suboptimality of each individual WT, which means that if everything was IID, that would imply a regret bound. But in general, we don't have a regret bound.
Oh,
we're relying on the regret bound of this WT to do something else, basically.
Yeah. So my question was, does it improve on AFKT, this recent AFKT bounds? Answer is no. Because it does not give a adversarial regret bound.
Yeah, not adversarial. Yeah. This is
definitely.
Okay, so what can we do with this beyond just using regular gradient descent? Well, we can try to apply a more interesting online learning algorithm. So what if we look at, say, Adagrad, right? Something that has an adaptive algorithm. So these are algorithms that have been built by online learning enthusiasts, let's say, who want to build algorithms that if the sequence of losses that are presented to the algorithm are somehow well-behaved in some arbitrary way, they will get lower regrets. And so if you take one of these algorithms and you plug it into this framework, you sort of immediately actually get a private algorithm that also has a sort of beyond worst case guarantee. And sort of I'm simplifying a little bit the expression, but what you'll end up getting is a bound that has some sort of negligible term out here, and then the privacy term is left unchanged, and then you get this sigma d over root t. And importantly, this is using the true sigma. So this again is something that is the variance in your gradients, sort of some unavoidable noise floor you should think of, but it's not something that we have to measure, right? So you might imagine that you should try to do this by first estimating sigma, doing some private estimation there. That's a little bit complicated, and then using that in some way to build an algorithm. We don't have to do that. We just immediately import the adaptive nature of Adagrad, and then this bound just sort of falls out of the algebra. We don't have to actually know what sigma is to get this done. As another example, we can use so-called parameter-free or comparative adaptive algorithms. So these are online learning algorithms that guarantee, as a worst case regret bound, for all comparators u, the bound will depend on the distance between u and some initial point w1 that you provided the algorithm. So this is a non-uniform regret bound. And if you use one of these and you give an initial point w1 that you think is somehow close to the optimal value, then with privacy, you can guarantee essentially the same result. You just port in this u minus w1, and it'll show up here in the place of some diameter bound. And the important thing about this is, let's say you're doing some sort of private fine-tuning, right? So when you do fine-tuning, you maybe pre-train on some public data, you get some w1 that you think is a good initialization. Why is it good? It's a little bit unclear, but maybe the reason it's good is that it's close to the optimal point, right? And so this bound will automatically get a better guarantee without having to sort of adjust itself depending upon that closeness. Okay, so there are some caveats I would like to make sure everyone knows. First is that our dependence on the constant h is wrong. It's a little bit incorrect. We do have a silver lining for that, which is that our privacy guarantee does not require convexity, which is usually is required by other SEO algorithms. And there is some open work here, which is to sort of move beyond the L2 norm. This is very commonly done in online learning. We haven't really pushed our analysis to go to that setting for SEO yet. Okay, so let me just summarize here. The key idea of this talk was to try to build an algorithm that takes any online learning algorithm and converts it in a black box way into an optimal private SEO algorithm. And we do this using this anytime online to batch conversion that automatically stabilizes the iterates, makes them very close together so that we don't have to add very much noise. And then the idea, hopefully, is that we can import a lot of these sort of huge amount of literature in online learning to try to build better private optimization algorithms. Okay, let me leave it there. Thanks, and any questions, I'll be happy to answer.
Thank you for the talk. I will turn off the recording.